Hello everyone, my name is Rishabh Bafna and in this video, let's continue with memory management. So in the previous video, we have seen um, memory management techniques, contiguous memory management techniques like fixed partition scheme, variable partition scheme, and we have seen non-contiguous memory management techniques like paging and multi-level paging. Okay. I'll just give you a quick glimpse of all these four techniques and then we'll continue to further techniques. Okay. So let me write memory management techniques. See, contiguous memory management techniques. We have seen it in previous lecture. Which one we saw? Fixed partition scheme. Next one, variable partition scheme. FPS, fixed partition scheme. Variable partition scheme, VPS. We have also seen some non-contiguous memory management techniques. Like first one, paging, then multi-level paging. All these four techniques we have already covered in previous video. We'll be covering this as well. Segmentation. Segmented paging. Okay. Finally, inverted paging is also there. Inverted paging. And finally, we'll see this one. What? Demand paging. So these are the techniques which we'll be looking at. Now, apart from this, we'll look into page replacement algorithms. See, page replacement algorithms. For example, FIFO, optimal page replacement, least recently used, most recently used. We'll look at a phenomenon called as Baladi's anomaly. Okay, and thrashing. Baladi's and thrashing. So all these things we'll look at in this today's lecture. So this will be kind of quick revision session for memory management, in which I'll cover each and everything in short. Okay, everything will be covered. So let's get started. So if you observe this fixed partition scheme, I'll just write title here, FPS. FPS indicates what? Fixed partition scheme. In this fixed partition scheme, what have we seen? So memory will be splitted into fixed partitions. Okay, this is limit register which indicates limit of that particular partition. This is partition, okay. Partition or hole, okay, or slot, something like this, okay. Now this is limit register which indicates limit of that particular slot. let's say 50 kb, 100 kb, 70 kb, 25 kb, 300 kb, something like this. There might be processes inside this, isn't it? Let's say P1 is here, P2 is here, P3, okay. P3 is here, process P3, P4 is here, P5 is there. Okay. In each particular partition or in each particular hole or in each particular slot, only one process can reside. That is what I have told. That is what I have mentioned in previous video. Only one process can reside in each partition. Okay, only one. So if you observe this one, if P1 goes to completion, okay, if P1 goes to completion, let's say new process arrives, let's say P6. P6 is of, let's say 30 kb. 30 kb. We can store P6 here, isn't it? We will store P6 here. Okay, I'll just change the color. Let me change the color. I'll store P6 here. P6 here. If you observe this 30 kb done. Remaining how much? 20 kb. 20 kb. 20 kb is free, isn't it? Now, even though that particular slot of 20 kb is free, we will not be able to put any other process inside it, isn't it? So that is what is called internal fragmentation. This is the issue of internal fragmentation. Internal fragmentation issue exists in fixed partition scheme. Done with this one. So this is what I have mentioned as well. Let's take a quick glimpse of variable partition scheme. So few points about fixed partition scheme you need to remember. First point, so memory will be divided into fixed number of partitions. In each partition only one process can reside, isn't it? Now, if there is only one process in each partition, how many processes can come at max? That the degree of multiprogramming is restricted by the number of slots or number of partitions or number of holes, so isn't it? Or slot, you can also call it as slot. Okay, or slot. Degree of multiprogramming indicates what? The number of processes which might be present at any point of time in main memory. That is called as degree of multiprogramming. So degree of multiprogramming is restricted by number of partitions because those many processes can only reside, isn't it? How many partitions are there? And that partitions is fixed partition scheme, size fixed. Now, even this point we have seen, limit register. There are two types of limit register. Lower limit register, upper limit register. Lower limit just stores starting address, upper limit ending address, stores ending address. That's it. This is all about FPS, fixed partition scheme, done with quick revision of fixed partition scheme. So just let's see next one. Variable partition scheme. Variable partition scheme. Variable partition scheme. So let's say these processes have arrived. Let's say 30 kb, 50 kb, 100 kb, 60 kb, 250 kb. So this processes arrived of this 30 kb. Process P1 arrived of 30 kb. We made a slot. Initially, that entire memory, there was no slot as such. 30 kb process arrived and we made this slot. Okay, done with this slot. 50 kb process arrived, we just made this slot, isn't it? Which? P2 slot. 100 kb process arrived and we made P3 slot of this 100 kb. P4 of 60 kb arrived and we made slot. P5, let's say 250 kb arrived, we made slot. So that way it happens, isn't it? Now, if you observe this one, let's say process P2 went till completion. Gone till completion. Okay, completed. It is not right now. Fine. P4 also gone till completion. And another process came. Okay, I'll mention which one is completed. Okay, just I told you, isn't it? No need to explicitly mention. P2 completed and P4 also completed. Fine. Now, if you observe this one, P4 also completed. Now, if you observe this one, if suppose a new process arrives P6, let's say P6, P6 process arrived with request, let's say 110 KB. Just for example, I am telling request. Process request P6 of 110 KB. What will happen? Will we be able to store process P6 into our memory? If you observe, 110 KB is not available contiguously anywhere. Here 50 KB slot is free because P2 done. 60 KB slot is free because P4 done, isn't it? But 50 plus 60 is 110. But 110 KB is available but not available contiguously. That is why we won't be able to satisfy this request P6 request. Are you getting it? We won't be able to satisfy this particular request. So that is what is called as what? This external fragmentation. External fragmentation. Done with it? I hope you are getting it. P2 and P4 completed. This 50 KB, 60 KB slot available now. 50 plus 60 is total 110 KB. Let's say new process P6 arrived of whose size is 110 KB, okay. Now we have to store P6 process into our memory. But can we store it? Obviously no, because that space is available but it is not available contiguously. That is why we can't store it. And this phenomenon, this problem is called as what? This problem, external fragmentation. This is called as external fragmentation. Memory is available but not available contiguously. Done. External fragmentation is there in variable partition scheme. To solve this problem of external fragmentation, what we did? We did compaction. This term I mentioned. Compaction. Do you remember what is compaction? I told in previous video. Compaction indicates that you either move all the process upwards so that in downwards, okay, in downside there will be freely available memory, free slots, all will be available downside. Either move it upwards or move all the process downwards so that free memory will be available upwards. Are you getting it? So free memory should be available at contiguous place. That's the motto, isn't it? We are just using compaction to solve this problem of external fragmentation. I hope you got it. Either move free that process upwards so that downwards free contiguous memory is available, or either move all this process downwards so that upwards free contiguous memory is available. That way that problem of external fragmentation is solved. Done. So that is what I mentioned. Compaction is not feasible because it interrupts all running process, isn't it? That is what I have mentioned. Now next one, variable partition scheme, quick revision over. Next one, let's see. Paging quick revision. Paging. What do you indicate by paging? See, I'll draw a diagram first and then tell you what do you mean by paging. So I told you about logical address space. This one is logical address space, isn't it? Logical address space. Logical address space indicates what? Secondary memory. Okay. Next one. This is physical address space. Physical address space indicates what? Main memory. Next question. Logical address space is divided into what? Answer, pages. Logical address space is divided into pages. These are pages, okay. So tell me, how many entries will be there in logical address space? How many pages will be there? How can you calculate it? Obviously, this number of pages will be number of, I think I should use another color. Let me just change the color. Okay. Number of pages will be how much? How can you calculate number of pages in logical address space? See this slot size, this entire slot size is, slot is called LAS, and this one page size. LAS by logical address space by page size. Logical address space divided by page size. You'll get number of pages. Done with it, done with it. Next question. Physical address space is divided into what? Frames. That is the answer. I told you last time. See. All these are actually maybe frames. Hashtag. Hashtag it just indicates number of, okay, frames. So how many frames will be there? Tell me. if this entire thing is frame, this entire, this complete slot is of PAS and this small slot is of frame. How many frames will be there? Obviously this PAS divided by frame size. It will be what? Formula. Physical address space divided by frame size. Done. Now, next one. We will be maintaining a page table. Okay, let me just change it. We will be maintaining a page table. These are page table entries. You answer my question fastly. How many entries will be there in page table? How many entries will be there? Entries will be equivalent to number of pages. Again, number of entries in page table. Number of entries in page table equal to number of pages in logical address space, in LS, in LAS. I hope it is visible, isn't it? These many entries will be there. How many pages are there? That many only entries will be there. Now, what is this? What is this one? This is page table entry. PTE, page table entry. What will be the size of page table? Tell me fastly. Next question. What will be the size of page table? Page table size. Answer fastly in comment section, okay? Try to answer it. Page table size. Number of entries in page table into page table entry size. Isn't it logical? Number of ENTRIES entries in page table into page table entry size. Let me rub this one. Where is eraser? Okay, what else do I have to rub? This one and this one. I think this seems good. Now, next question. See, a CPU or processor will generate what? Tell me. CPU or processor will generate logical address. Logical address. Logical address indicates what? If this is logical address space, we are pointing to a page, and within that page, which word we want to refer. That is what we will be pointing, isn't it? We are going to a particular page, and within that page, which word CPU wants to access. That it will specify. That is logical address. See, logical address consists of this P and D. What is this P? P is, okay, page. I think I should move here. Fine. Page number. What is this D? Tell me fastly. Page offset. Page number and page offset. So this P, from this P will, number of entries in page table is equivalent to number of pages. So 0, 1, 2, whatever it might be, will go to a particular page table entry, whichever we want to refer. Let's say page is 5, we'll go to 5th page table entry, isn't it? Now, within that page table entry, what is stored? That is next question. Frame number is stored. Okay, let's say there is frame number, some particular frame number is there. That frame number we got from this page table entry. What is it? Tell me. This is F. D will be as it is. What is this entire thing? Frame number and D, frame offset. This is physical address. This D and this D both are same only. I hope you are getting it. This D and this D both are same only. Same only. Now, conversion of page table, conversion of logical address to physical address is the work of paging, isn't it? Conversion of CPU generated logical address to physical address is called as paging. Very easy, done with paging concept. From now, once you get the frame number and frame offset, what will you do? you'll go into that particular frame number, isn't it? Just have a look at it. Once you get that F, what will you do? You'll go into that particular frame number, okay? And within that frame, that particular page will be there. Next question, page size, frame size same or not? Same only. Page size is same as frame size. When it is in logical address space, we refer it as page. When it is in physical address space, we refer it as frame, but both sizes same only. At the end of the day, we bring pages from LS to PS, isn't it? So same only. Now, we are referring to a particular frame from physical address space. Within that frame, what will be present? This slot, what will it contain? Page or okay, frame. Within that frame, what do you want to access exactly? We want to access some word. Where will it be specified? It will be specified by this D. Are you getting it? This D indicates what? Frame offset. This D indicates what? Page offset. Both are same only because page size, frame size is same. Are you getting it? Done. So we can access that particular word. We can access that particular word from particular frame. Done. So the conversion of CPU generated logical address to physical address is called as paging, and that's it about paging. There's no external fragmentation here. Let's see next one, what I mentioned. Multi-level paging. Multi-level paging. Multi-level paging. If you talk in terms of machine learning, MLP will indicate multi-layered perceptron. Multi-layered perceptron. Right now, I just wrote it shortcut for multi-level paging. We saw the paging concept. Now, multi-level paging. We are maintaining multiple page tables. Okay. 2 level, 3 level, 4 level, so on. Okay. Now, let's see. Let's draw the diagram. Okay. You please watch carefully. I think I can use shapes as also. If you see this one. Okay. Let me use shapes. What is this? This is logical address space. What is this one? This one is physical address space. What is this one? This one is page table. What is this one? Okay, I'm maintaining 2 page tables right now. Done. I think this one is better using this. So this is logical address space. Logical address space is divided into what? Pages. Physical address space is divided into frames. This is page table, our original page table. Number of entries in original page table is equivalent to what? Number of pages. I'll tell you what it is, why we did it. Just wait for some time. Done. I think I'll be using these shapes from this current point stamp, timestamp, isn't it? So let's see this one. So if you observe, what is this? This is CPU. CPU will generate what? CPU will generate logical address. Logical address. Now logical address consists of page number and page offset. Because at the end of the day, we want to refer to a page from logical address space, isn't it? This is physical address space. This is, okay, let's see. This was page table R, original. Page table, the one which I told you in during paging, same only, this is same. Now, when will you apply further paging? See, first point, need to remember, page table is stored in main memory. Now, next question. If it is stored in main memory, it is stored actually where? Where is it actually stored? Obviously, main memory, there are frames. It will be stored in frame. Now, if frame size is this much, okay, if frame size, let's say, frame size is 100 KB and your page table size is, let's say, 800 KB. Will your page table fit in a frame? Yes, your page table will fit in a frame. No need to do further paging. Okay, but what if your page table frame size is 1000 KB? First example, see, page size. Page size is 1000 KB and your page table size Page table size 100 KB. Let's say this example. Okay. Your page table will fit in a page. No need to worry. Page size or frame size. Okay. Frame size. Your page table will fit in a frame. But what if your page table size is 1100 KB? Hey, your page table won't fit in a page or frame, isn't it? You'll have to do further paging. So that is the concept of multi-level paging. If you observe this one, let me. Oh, I deleted it. How can I undo? Got undo. Eraser. See, if you observe this one, when are we performing paging? If that page table size exceeds frame size, then only we are performing paging, further paging. Let's say this frame size. Let's say this frame size. Okay. Within this particular frame, these many slots are there. This particular frame, these many slots are there. So on. This is the last one. So this page table is fit in these many frames, isn't it? Now what will happen? What will we do? Okay. We'll maintain another page table with starting addresses of this one. It will point, this slot will point to this one, this slot will point to this one, so on, okay? This last slot will point to this one. This is what we'll do. This is what? This was our original page table, and this indicates what? Page of page table. This is page of page table. This is page of page table. This is, okay, undo. This is page of page table. This was the entire original page table, isn't it? We divided into pages of frames, okay. Now, how many such frames are there? That many entries will be there in this newly generated page table. What is this page table called? This is page table of page table. This is page table of page table. Done. This is also called as what? Outer page table. OUTER. Outer page table. Or first level page table. First level page table. This is also called as, okay, specifically this one, okay, this one I am talking about. Page of page table. Or inner page table. Inner page table. Or second level page table. Or second level page table. This one I am talking about, okay. Page of page table. Done. So when are the question arises, when are we doing? When will we do further paging? This is the question. When that page table size exceeds, when page table size EXCEEDS exceeds frame size. Frame size or page size same only, isn't it? I told you. Because page table will be stored in main memory, and main memory, if it is stored in main memory, it means it is stored in frames. It means it will be stored in that particular frame, so it should be less than frame size, isn't it? Less than or equal to, isn't it? So when page table size exceeds frame size, then we'll do further paging. This is the question, and okay, I think it is. This is the question, and this is the answer. When will we do further paging? When page table size exceeds frame size, do further paging. So what is the condition which needs to be satisfied? Condition which needs to be satisfied. Tell me. Page table size should be less than frame size. Less than or equal to, okay, frame size. If this is there, no need to worry. Less than or equal to, okay, whatever. If this condition is satisfied, no need to do further paging, isn't it? Done. Next one. Here I wanted to mention this one. This logical address is there, P and D. Now, this P will point to what? P indicates page number. How will we get page number? So first we will point to entry in page table of page table. Then you will point to entry in that particular page of page table. These two entries are just P1 and P2. Let's say I draw something like this, P1 and P2. From here, we'll just check that P1, okay, P1 entry. From here, we got that starting address of that particular page of page table. We went there. Let's say we went there, okay. I think I should undo this one. Okay. Let's say this is that particular entry. We got this particular frame number. Starting address of that page of page table. We went there. Within this, we want to get to P2 slot. We went there. In this slot, what will we get? We will get frame number. Frame number. So you will get frame number. This is F. Very easy, okay. This is frame number and this is frame offset. Once you get frame number, what will you do? Once you get frame number, you will go to that particular frame. You'll go to that particular frame and you will just access that particular word, whatever it is. Done. That way, isn't it easy? If you observe this one, what is it? Let me change it to, this one is logical physical address. At the end of the day, what is happening? Logical address conversion to physical address. Paging or multi-level paging, whatsoever it might be. That is what is happening, isn't it? So this is all about multi-level paging. Done with multi-level paging. Now let's see next point. See, I'll just show you first slide. We revised fixed partition scheme. We did the revision of variable partition scheme, contiguous memory management techniques. Now we revised paging. Then we revised multi-level paging. Now let's see segmentation. Let's see segmentation, okay. This time I didn't made any kind of PPT. I thought of telling it in the form of diagrams so that you will understand it properly. So just because I had to draw diagrams, see, instead of mentioning diagram beforehand, I drawn the diagram live here. So why I did it? Because you could draw it along with me live. So if I could have drawn it earlier and explained and just changed the slide, you would not have written it because it would take time, isn't it? If I draw it, you can draw simultaneously along with me with the same speed, isn't it? Somewhat same speed, okay. That's it. That is why I have drawn diagram this time. Let's see segmentation. Or before segmentation, let's see inverted paging. So maybe inverted paging, INVERTED, inverted paging. See, first point that I want to focus. What is that point? This is logical address space. This is physical address space. Okay. Okay. Done. So let me just draw that slots. Where is that line? So logical address space is divided into what? Tell me. Pages. Logical address space is divided into pages. Physical address space is divided into what? Frames. This is page table in case of inverted paging. Okay. So okay, let's get started. This is LS, logical address space. This is physical address space. Logical address space is divided into pages. Physical address space is divided into frames. CPU generates what? Tell me fastly. CPU generates logical address. See, in case of paging, process can be big, isn't it? So that it is further splitted into multiple pages. Now, for every process, we need to maintain a separate page table in case of paging. but to just to avoid that overhead of maintaining big page tables, isn't it? So many page tables. We just use inverted paging, in which we don't have to maintain like so many page tables. If you observe this one, this is inverted page table. INVERTED. Inverted. Shouldn't mention like that inverted page table. I'll mention page table only. Page table in case of inverted paging. What does it contain? 0, 1, 2, so on. Okay, whatever it is. This number of entries in inverted page table. I should mention inverted page table only. Let me just delete it. Yeah, I think you got to know. Inverted page table. Number of entries in inverted page table is same as number of frames in physical address space. Earlier, what you saw in paging, number of entries in page table is same as number of pages in logical address space. Now your page table, number of entries in that page table is same as number of frames. That's the difference, isn't it? This one and this one, these many entries, both are same. Done. Process ID, PID, and page number. That process can be divided into multiple pages. No, which process you want to refer, within that process which page number you want to refer, that information is stored here. Are you getting it? See, let's say you want to refer to process 5 page number 2, just for sake of example. Process 5 page number 2 you want to refer. What will happen? Okay, this is what process 5 page number 2. Process 5 page number 2. This is PID, process ID. This is page offset. This is page number, this is page offset. What is it? Tell me fastly. What is this one? Process ID. Are you able to look at it? P. What is P? Page number. What is D? Page offset. Done. Which process you want to refer, within that particular process, which page you want to refer, within that particular page, which word you want to refer. Done. That is what your logical address space will be. This is logical address. Logical address will be. This will be in bits, isn't it? CPU will generate logical address. Done. Now 5.2, process 5, page 2 we want to refer. We'll just scan it. We'll see where is process 5, page 2. Oh, we found it. We found it here. Process 5, page 2. Now what is that frame number? Okay, frame number is 2. You got that frame number. You got that frame number. You just go. Frame number. This is F. This is frame number and this is frame offset. This is physical address. Are you getting it? You got that frame number. You can go to that particular frame, isn't it? It's that easy. You can go to that particular frame, that particular slot. I think I should rub it. Just a second. You can go to that particular slot and just access that particular frame offset. I mean, access that particular word in that frame. This is D. F, you can go to that F, whatever it is mentioned, frame number. Within that frame number, you'll have frame. Frame, there will be words, isn't it? Which word you want to refer, that will be referred by what? D. Word of frame offset, isn't it? Done. So this is how you can get it. If you observe this D and this D, same only. Done. That's easy, isn't it? This is the concept of inverted paging. Done. Now, few questions. Number of entries in inverted page table. Answer fastly. Answer in comment section. Number of entries in inverted page table. Same as number of frames in physical address space. What will it contain? Process ID and process number. Now, another question. That's it. This is the only difference between that what we have learned earlier in paging and this inverted page table. This in conventional page table, number of entries in page table is same as number of pages in logical address space. In inverted page table, number of entries in page table is same as number of frames in physical address space. That's it about inverted paging. Inverted paging done. So if you observe this one, I'll just put a tick mark on what we did. Inverted paging done. You have a look at this. Segmentation, segmented paging, demand paging. 3 remaining. Let's do it fastly. Okay. Let's see segmentation. Segmentation. TA. Segmentation. See, in this case of segmentation, what is happening? In logical address space, there will be segments. Okay. In physical address space, that segments will be brought from logical address space to physical address space. Will maintain segment table. Okay. CPU will generate logical address. This will be logical address. Okay. Is there any other shape? Okay, this one. Okay. I'll do it later. Okay, I'll do it later. Now, see, this particular logical address space is divided. Okay, now if you observe, logical address space is divided into segments. I mean, there are segments in logical address space. These are segments. Let's say segment 0, segment 1, segment 2, segment 3, something like this, okay? Just I'll give you a quick glimpse of what is happening. We are bringing these segments from logical address space to physical address space. This is physical address space. We are bringing the segments. Let's say base address, okay, 0, size, this one 500, this one let's say 1000, this one 1200, this one 1500, something like this. Okay. Now if you observe this one, this is segment table. Segment table. See, it is very logical. If you observe, previously in logical address space we had pages. That is why we maintained page table. Now in logical address space there are segments. That is why we are maintaining segment table. In which particular segment we want to go, isn't it? That is what we will maintain. All these things. If you observe this one, 0, 1, 2, so on. Okay. CPU will generate what? CPU will generate logical address. This entire thing is logical address. Now logical address will consist of what? See, you want to go to a particular segment. Within that segment, what is that segment offset? Okay. What exactly you want to refer? That will be mentioned by CPU. Okay. That is segment number and segment offset. I hope you got it. What is this S? What is this D? Tell me fastly. S indicates what? Okay, I think I should. Segment number. Segment offset. See, this segment number you want to access. Now you will go to that particular segment number. Let's say you went to that particular segment number. This is that particular segment number. You went to that particular segment number. What will it contain? It will contain base address. Base, okay, just a second. It will contain base address. Okay. base address and size of that particular segment. Base address and size. If that base address will be maintained, isn't it? This will be base address. So let's take example X. We want to refer to segment X. We went here, base address of segment X. This way it is good to explain, isn't it? Base address of segment X, size of segment X, isn't it? Done. Now we want to refer to this particular offset D, isn't it? If D exceeds that size, there will be issue. If D doesn't exceed size, there is no issue. This is length, isn't it? Length of that particular segment. If D exceeds that length, there is issue. D doesn't exceed that length, okay, no problem, we can access it. Observe here, what will happen? We will check, see, we'll get D from here. D. Now if D is less than the size of segment, isn't it? This less than size of segment, what will happen? We will add base address, this base address, we'll add this base address with D and then go to that particular point, access it. Done. I hope you are getting it. Let's say this indicates segment X is stored here. We'll go to that particular segment offset, isn't it? We'll just access that segment offset. Done. If D is less than size of segment or length, then we'll perform base address plus that offset, and we'll go here at that particular location, base address plus D, and we'll access it. But what if it doesn't exceed? No, if no, okay, if yes, then do this one. If no, then we cannot continue further. We cannot continue further. We are trying to access something which is not there within that segment. See, logically, if you think this way, this one is your segment. This is base address. This is base address of segment, base address. You are trying to access base address plus that offset. Offset, you are coming here at this point. Offset, you should come here less than length. This is length, isn't it? Length or size. You should come here, here, or here. Worst case. You are going out of that size, isn't it? How can you access something which is not there? Let's say you are exceeding the segment size, isn't it? You are accessing something which is not there. So obviously it will be trapped to OS. Let me delete this one. Okay, delete. If yes, then add base address plus that offset. And if no, then we cannot continue further execution. They is trapped to OS. Now this is the entire concept of segmentation. Segments indicate, logical address space will consist of segments. For example, segment 0, main function, segment 1, some function, SUM, any functions, anything can be there, all these segments. Because why do we apply segmentation? Because paging do not apply user's view of this memory allocation, isn't it? User's view does not follow user's view. According to user, main function, all these functions, isn't it? So in order to follow user's view, we'll apply segmentation. We'll bring that segments from logical address space to physical address space. Now, if we are bringing segment, it will be stored anywhere here in physical address space. Where exactly it is stored? How will we know? We'll take base address and we'll add that offset. But when will we do it? When that offset is correct, isn't it? From X, from this S, we'll get segment number. Okay. This segment number, we went here. Okay, what is base address? Oh, we got it, okay. And then what is size? We got it. We'll go there, just check it, done. So that is how it will happen. So if you have any doubts, do let me know. I'll check the comment section. Maybe you just try to tell me if you are having any doubts. Do let me know. ACE Engineering College, live, okay. Live chat, presentation is good. Fine, I think no comments as of now. So let's continue further. Fine. Done with segmentation. Now let's see next point, which is that segmented paging. We are done with segmentation. Now let's see segmented paging. So this one will take some time, but I'll try to do it fastly. See, there will be logical address space, there will be physical address space, there will be page table of segment, there will be segment table, isn't it? CPU, the logical address, so many things are there. See, what I want on this pen. Logical address space will consist of segments. Same only. Segmented paging also same only. Logical address space will consist of segments. But the segments will be, this segment 0, segments will be further divided into pages. Are you getting it? It will contain, I think I should write it this way. Segment 0. Segments will be further divided into pages. Segment 1. Segments will be further divided into pages. Something like this. All these are segments. S, Z, something like this. So randomly I've written something. Segment only, all this. Now, these pages will be brought from LAS to PAS. Earlier what we did, see, very logical. When we deal with segmentation topic, we brought the segments from logical address space to physical address space, that complete segments. But what if that segment size is too big, isn't it? That is why we split that segment into pages and we bring that pages from logical address space to physical address space, pages of that segment. That is why we need to maintain separate page table of segment. So this page table of segment. These are pages, okay, these are pages. This is physical address space. See, it is very logical. If you observe this one, you please concentrate properly. Try to make notes along with me. This is segment table. Now, if you observe this one, CPU will generate what? CPU will generate logical address. Logical address. Logical address will consist of what? Segment number and segment offset. Logical address will consist of what? Segment number and segment offset. We'll go to that particular segment number. Okay, we'll go to that particular segment number. You tell me what will it contain? This will be base address. This will be size. Done. We'll get that base address. We'll get that size. Isn't it? If that D exceeds size, then there is issue. If D doesn't exceed size, there is no issue. If you observe this one, what will we do? Same thing only. See, if D is less than size, if that segment offset is less than size, is it visible? If that segment offset is less than size, what will we do? We'll continue further execution. We got D from here. We got D from here. We got D from here, and we got this one. Okay, size. Now, if that D is less than size, then okay, no problem. Just add it. D. You add D with what? This base address. You add D with base address. Base address plus D. Base address plus D. Okay, just a second. Base address. That is where you want to go, isn't it? But then, if that happens, see how will you tackle this problem? Just have a look at this one. You'll take another table. See, have a look at it. Earlier you had what? S and D. S indicates what? Segment number. D indicates what? Segment offset. But this D will be further divided into what? That segment is divided into further pages. Okay, which page of segment are we referring and what is that offset? That is what we will deal with. Are you getting it? Which page of the segment, okay, this D and this D is not same. Let's say P1, D1, something like this. Okay. This D is further split into P1 and D1 because segmented paging, within that segment there are pages, isn't it? If there are pages, which page are we actually referring and that offset, page offset. And finally, this entire thing will get converted into what? Okay, I think I should write it here. From all this, we'll get what? Which frame it is present and what is that offset, frame offset. And from that, we'll go to that particular frame and we'll access that page. If you observe this one, okay, something like this. Here, we'll have that particular frame, F and D1. P1, D1. Which page you are accessing? This both are same. Okay. This entire thing. Okay, what is it? Let me change the color. This entire thing and this D, this same. Size same, isn't it? This D got splitted into P1 and D1. Now you'll go to that particular page. Okay. Okay. This P1 will indicate what? You'll go to that particular page. How will you go to that particular page? That page will be present in physical address space. Where? We want that frame number. You'll go to that page table of segment and you'll get this frame number. You'll get this frame number. And once you get that frame number, you'll go to that particular frame and access that. This is frame offset. And this way you can do it. This is how segmented paging will work. So, I will give you a quick glimpse of what we have done from paging to segmented paging. Just have a look at it. See, paging, okay, paging. In this paging, there was logical address. Logical address. Page number and page offset, which got converted to physical address. Which got converted to physical address, frame number and frame offset. Done. This is what happened. Done. Now, let's see what we did in multi-level paging. Multi-level paging. Multi-level paging. In case of multi-level paging, we had that logical address. Page number and page offset. We converted it to what? Tell me. This page number, we got that page number, how? Depends on the number of levels. If there are, let's say, 3 levels, okay, if there are 3 levels, how can you convert that page number into frame number? You'll see that page table, isn't it? You saw a page table and then, okay, if that page table, you need to see another level, you saw that level, you need to see another level, you saw that level. Finally, you will get that frame number. Let's say there is 2 level paging. So you will access outer page table, okay, entry in outer page table and then entry in inner page table. This P is, okay. this P will get splitted into P1 and P2. From this you will get F. Once you get F, what will you get? This D is same. You will get that what? Physical address. If you observe this, F and D. Done. This is how multi-level paging will work. Next one. Segmentation. Let's say segmentation. In segmentation, we just got it by adding, okay, S and D was there. You got physical address just by adding base address plus offset. Base address of segment plus segment offset. That is how you got. You got physical address by that base address plus segment. So that's about segmentation. And next one, what we have seen, tell me fastly. We have seen segmented paging. Let's see segmented paging. Segmented paging. S and D. Which segment you want to go? Within that segment, what is that offset? This is logical address. Okay. Now, if you observe this one, just have a look at this one. Just look at the diagram, isn't it? SD got converted to P1, D got converted to P1, D1, isn't it? This is D, isn't it? D got converted to P1, D1, let me write it here. D will get converted to, see, segment and segment offset. Segment is divided into pages. You got to know which segment you want to access. Now which page you want to access, that you will get to know. How? Page number of that segment and then segment offset. Page offset, okay, or frame offset. Done. Now, from this you finally got physical address, which is frame number and then frame offset. Done. So this is how it happened in what? Segmented paging. D got splitted into P1, D1. See, segment offset. Which page you want to refer? Within that page, what is that page offset? Now, that page, you saw page table of segment. From that page table of segment, P1 entry, you saw P1 entry and you found F. Frame number. That particular page is present in which frame? You converted P1 to F. That offset will be same, D1, D1 here. Done. You go to that particular frame and you just access that word of that frame, whatever is mentioned, D1. Done. You'll get it. Whatever, CPU will get it what it wants. Logical address. So this is how logical address got converted to physical address. So do let me know if you have any doubts. I'll see the chats once. Just see this entire thing all at once and do let me know if you have any doubts. We have seen paging, we have seen multi-level paging, we have seen segmentation, we have seen segmented paging. Oh, okay, we have also seen inverted paging, isn't it? This one, let me write it. Let me change the color. What is it? Which color? Let's say blue is remaining now. Inverted paging. I think this may not be visible. I'll take yellow again. Inverted paging. Inverted paging. In case of inverted paging, I told you what we are doing. We will maintain inverted page table which will contain what? This process ID. See, logical address PID. Logical address consists of process ID, page number and page offset. This is logical address. Logical address gets converted to what? Which frame, what offset. Done. This is physical address. Done. This is how that conversion is being done. So inverted page table will consist of what? Process ID and page, which page you want to refer. Done. If you get that which process ID, which page is present in which entry of that inverted page table, that entry number is itself frame number which you will be referring. You got that frame number F. Done. This is how you will convert that logical address to physical address. Paging, okay. Conversion of CPU generated logical address to physical address is called as paging. Done. Done with all these things, okay. If you have any doubts, do let me know, okay. I'll just see the chat sections one. I think, okay. No, not right now. Fine, nothing is there. So let's get back to this one. I'll just tick mark all this. Isn't it? Let's just tick mark whatever we have completed. See, paging done, multi-level paging done, segmentation, segmented paging done, inverted paging also done, demand paging is remaining. Okay. Let's say segmented paging diagram is very important. Okay. Just this is important. Segmentation, and see in segmentation, if that size exceeds, then this trap to us, we cannot continue further. If that size doesn't exceed, we'll continue. Okay, base address plus D. Here I think I mentioned base address, no? So this D will go, isn't it? No need of this addition and all this. Base address, no need to do add this one. This one is wrong, okay? This one is wrong. No need to add it, isn't it? Just directly you got, if the D is appropriate, if D is less than size, that offset is less than size, you can directly get this P1 and D1 from this D. This length is same. I think I should mention like this. Maybe where is rubber eraser? I'll mention something like this. Done. I'll write like this. Let's say, if yes, go here. D. Yes. If no, we cannot continue further. We cannot continue further. See, once we have base address, we'll create that particular page table of segment. Within that page table of segment, we'll have to check for that segment offset, isn't it? From D we'll get it, D segment offset. Which particular page you want to refer? What is that particular page offset or frame offset, whatever it is. From this, okay, just quick corrections, small corrections I made. I think that's good. This one is correct now. Let's see next one. Demand paging. To see demand paging, just observe this one. See, it is very easy. You please concentrate properly. It is very easy. You see, this is logical address space. This is physical address space. This is page table, isn't it? This one CPU. It generates logical address. Logical address from page table it will get converted to what? Physical address. I think I need some space here. Rubber. Eraser. Okay, just rub it. This gets converted to what? Physical address. Done. So if you observe this one, this is logical address space. Logical address space is divided into what? Pages. Physical address space is divided into what? Frames. Page table. Okay. This is page table. Number of entries in page table is equivalent to what? Number of pages in logical address space. Done. Okay. Look here now. Everyone please concentrate. This is CPU. CPU will generate logical address. CPU generates logical address. Logical address consists of page number and page offset. You'll refer to that particular page, okay, in page table. This is page table. You'll get frame number, isn't it? You'll get frame number F, and that offset is there. This and this D is same only, okay, not different, okay. You got that frame number, you went into that particular frame, you access that particular word number of that particular frame or page. Done. This is how it works, isn't it? Now, okay, this is physical address space. I forgot to write it. Physical address space, this is logical address space. Okay. Now, observe here carefully. What if that particular frame number is not, okay, for that particular page there is no frame number here. That entry is not there, isn't it? Then it indicates what? See, here let's say frame number is present, isn't it? Some value is present. Here also present. Here it is not present. Here also present. Here it is present. Right now it is present. That is why we went there. What if it is not present? What if this was the case? It is not present. What will happen in this case? We want to refer to page, let's say X. We want to refer to page X, we got that page X. But when we referred page Y, we didn't got that page Y. What will we do in this case? Tell me. We have to bring that particular page Y from logical address space to physical address space, isn't it? Because just because it is not present, what we'll do? We'll stay there and cry. No, we can't do it. We have to bring that page from logical address space to physical address space. How will we bring it? Just see, this is on demand. This all happens on demand. There is demand for page Y, just bring it into physical address space. Then access it. This is the concept of that demand paging. If you observe this one, let me rub it first. Okay, rub all these things. I'll draw a diagram properly. Oh, issue. Oh, I think let's delete. Okay, I can't delete it. Let me not delete it right now, okay. Everything is going, okay. So, see here. We want a particular page, we went there. What if that page is not present? Isn't it? Well, if that page is not present, what will we do? I will change the color. First of all, I'll change this color so that I can show you. If that page is not present, what will we do? See, we refer to this particular page. This page is not present. Okay. First step, step one, first step. Now, if it is not present, we'll tell OS. We'll tell OS that that page is not present. If that page is not present, what will do? We'll tell to OS, step 2. OS will try to bring that page from logical address space. We'll point to logical address space. We'll go to logical address space, that particular page. We'll get that particular page, okay. We will bring that particular page from logical address space to physical address space. So step 2, this is step 3, this is step 4. We'll bring it in physical address space, that particular page. Done. And then we'll update that page table entry. This will update it, isn't it? We'll update it. Now, this is step 5. We'll just, and then we can refer to it. So this is how it will happen. Okay. So on demand, if that particular page is not present, we'll bring it from logical address space to physical address space. This is called as demand paging. Very easy. On demand it is happening. So Windows practically follows demand paging. Windows Linux all practically follows demand paging. So that is the concept of demand paging. If that page is not present, we'll have to bring that page from logical address space to physical address space. How will you know that page is not present? Within that page table entry, you won't find that particular frame number, isn't it? Okay. Done with this one. Now, next question arises. Okay, before that, I'll just tick mark this one. Okay. I'll tick mark this one, demand paging. We have covered fixed partition scheme, variable partition scheme, paging, multi-level paging, segmentation, segmented paging, inverted paging, demand paging, all of this, isn't it, in one video itself. So I hope this video is very beneficial for all of you. This live class. Okay. Now we need to see this concept, page replacement algorithm, where this page replacement algorithm comes into picture. If you observe this one, okay, I just crossed the limit. Okay. See there. We brought that page from logical address space to physical address space. Oh, okay, we have to store that particular page in which particular slot of physical address space? That question arises, isn't it? Any random slot will we fill it? No. There must be some algorithm, isn't it? That is called as page replacement algorithm. If there is something filled here, okay, there is something filled here, we'll just replace it with this particular page. Are you getting it? Page replacement algorithms comes into picture. What are different types of page replacement algorithm? First in, first out, optimal page replacement, most recently used, least recently used, something like this, isn't it? Fourth. So we'll see this page replacement algorithm. See, CPU is generating logical address. When it is generating logical address, it will consist of these two things. You observe this very carefully. Okay, observe this very carefully. Page number, page offset. What is this? This is page number. What is this one? Page offset. I think I forgot to write demand paging. Demand paging. I'll write it somewhere. Demand. Better to write in center. I think center. I can't write. I'll write it here. Okay. Demand paging. Demand paging concept. I taught it here in this slide. Okay. Now you tell me. CPU will generate logical address which consists of pages. Okay. Page number and page offset. Page number. I am referring to page numbers right now. Right now I'll be referring to a string of page numbers. Okay. Reference string. This is a reference string for page replacement algorithm. Page. Okay, just a second. Page replacement algorithms. We'll see FIFO, first in, first out first. FIFO first, okay. The reference string which we will be using is, so I'll take some reference string random, okay. These are reference string of page numbers, okay. Reference REFERENC, reference string of page number. This is a reference string. Let's say 27 this is 0, okay, 27105 6 7 2 1 7 5, something like this. Okay, this is the reference string. If you use FIFO, okay, what will happen? Let me do it. See, let's say there are 4 frames. 1, 2, 3, 4. Okay. 1, 2, 3, 4. 4 frames are there. If there are 4 frames, okay. Physical address space consists of frame. Let's say if we are considering 4 frames. 4 frames example. 4 frames example. 4 frames. Consider 4 frames right now. You are referring to page 2. You are referring to page 2. Page 2 present? Not present. So it is miss. Miss. You'll bring it in main memory. Okay. You are referring to page 7. Is page 7 present? No, not present. You'll bring it into main memory. Page 1, not present. You'll bring it here. Okay. Page 1. Again 0. Again miss. You'll bring it here. Now 5. Is there 5? No, miss. So 2 came first, replace it with 5. 6. 6 not there, 6 here. 7. This also miss. 7. It is not there. 7 miss. 2. 2 is there? Not there. Again miss. 2 is miss. 1 is there? 1 is not there. Again miss. 1. 7. Page 7 is there? Yes, page 7 is already there. Page 7 is hit. Page 5 is there? No, page 5 is not there. See, replace 6 with 5. This is how that FIFO, first in, first out algorithm will work. Whoever came first went out first, isn't it? So FIFO, this was of FIFO. First in, first out, page replacement algorithm. Next one. I think I should take some better reference string. There are lots of misses and very less hits. Let's take some other example. Let me take another reference string. Just to explain you optimal page replacement, let's take another reference string. So that will be good. So we are about to end the lecture. Few things only left. We'll just end it fastly. See. Reference string. Let's say reference. So 1, 3, 2, 4, 5, 3, 1, 2, 1, 4, 3, 5. Something like this. Okay. Now how will that optimal page replacement algorithm work? Just have a look at this one. If you see this one, this divided into 4. Consider 4 frames. Okay, you try it out with 3 frames. You try it out with 2 frames, 4 frames, 5 frames. Okay, different frames. Okay, let me consider 4 frames here. 4 frames. See, one is one there? Tell me fastly. Is 1 there in physical addresses? No, it is not there. We have to bring it. Miss. 1 done. Miss. 3 there? No, not there. 3 miss. Okay. 2 there? Not there. 2 miss. We have to bring it. 4 is there? No, not there. 4 is miss. 5 is there? Not there. Now, in optimal page replacement algorithm, replace the one which is least used in the, if you observe this one, let me not complete the sentence immediately. I'll explain you and then I'll complete that sentence. See, 5, we have to see 5. Now, in optimal page replacement, what will happen? See, 1, 3, 2, 4. Look for 1, 3, 2, 4. 3 is there. 1 is there. 2. Okay. 4 is not used for longer time, isn't it? The one which is not used for maximum amount of time. So 3, 2, 1 will be used immediately. 4 will be not used immediately. At last we'll be using it. Among this all available. In the future, we are seeing that future, okay, whichever page numbers will be referred by CPU, we are looking at it. In the future, which one will be last used? Last referred, isn't it? 4 will be the last referred in the future among 1, 3, 2, 4. 3 will be immediately referred, 1, then 2. Okay, 4 will be last referred in the future. So replace that 4, replace that 4 with 5. So I'll just write it 4 with 5. This was miss. But which one to replace? You got it. Page 4 with page 5 replace. 3 is there. Okay, 3 is there. Hit. 3 is there. 1 is there. I think I should rub this one first. Let me rub this 3. Let me rub this one. Okay. Now let's continue. 1 is there. 1 is there. Hit. 2 is there. Okay, 2 is there. Hit. 1 is there. Hit. 4 not there. Now 3, 5. 3 and 5 will be referred. 1 and 2, just replace anyone, no problem. Even if you replace 2 or 1, there won't be any effect on page faults as such. So if I cancelled 1 and wrote 4 here, done. 4 was miss. Then 3 already hit. 5 already hit. So you saw this number of page faults. How many page faults are there? 1, 2, 3, 4, 5. 6 page faults are there. Number of page faults, 6 in this case. Optimal page replacement with 4 frames. You see with 3 frames, you see with 2 frames. Try it out. How many page faults are you getting? How many page hits are you getting? Done. Page hits 1, 2, 3, 4, 5, 6. 6 page hits. 4 page. Okay, 1, 2, 3, 4, 5, 6. 6 page faults. Done. Done with optimal page replacement. See, we have to see these 4 techniques, among which we have seen 2, and then we'll end the lecture. FIFO done. Optimal page replacement done. Now let's see least recently used and then most recently used. We'll take the same reference string. I think that will be good. Which one? This one. But I'll just change the color. That's it. I'll change the color. Four frames. You can try it out for 3 frames at home. Okay. Now this one is most least recently used. Least recently used. Okay. 1 page fault, 1. 3 page fault, bring it. 2 page fault, 2, bring it. 4 page fault, bring it. From logical address space to physical address space. 5, again page fault. Which one will you replace? Which page will you replace? Tell me fastly. Least recently used. If you observe this one. In optimal page replacement algorithm, we see the future and the one which we will not be using immediately, will be using at last. That page will be replaced. In least recently used, we'll look backwards. The one which is not used recently will replace that. I mean, the least recently used will be replaced. Same name itself says the least recently used will be replaced. If you look at previous history, where are we right now? We are at 5, isn't it? 4 recently used, isn't it? 2, 4 recently used, then 2, then 3. Okay, 1 is least recently used. Replace 1 with 5. I hope you have got this one now. Okay, 3. Now 3 hit. 3 is there, hit. 1, okay, page fault is there. 5, 3, 2, 4. Just see 5, 3, 2, 4. Among this, which one is least recently used? 3, 5, 4. Okay, 2 is least recently used. Replace 2 with 1. Done. Now 2. Is there it hit? No. Page fault. 5, 3, 1, 4. 1, 3, 5, 4. 4 is least recently used. 4 with 2. Replace it. Done. 1 hit. 1 hit, isn't it? It is there. 4. Is it there? No, not there. 5, 3, 1, 2. Among this, which one is least recently used? 5, 3, 1, 2. 1, 2, 3. 5. 5 is least recently used. 5. Replace 5 with 4. Fault. 3. Tell me fastly. Where is 3? 3 is here. So it is hit. 5 is again miss. 4, 3, 1, 2. Among this 4, which one is least recently used? 4, 3, 1, 2. 3, 4, 1, 2. Okay, 2 is least recently used. Replace 2 with 5. This one is page fault. Tell me number of page fault. 1, 2, 3, 4, 5, 6, 7, 8, 9. I mean, around 9 page fault. Just cross verify it. Around 9 page fault. 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 page faults. Page hits how many? 1, 2, 3. 3 page hits here. In case of LRU. Last one, last point of this session. Last point of this session. What is it? Most recently used. I'll use white color. Last point of this session. Most recently used. Most recently used. Let's take 4 frames. 4 frames only for now. See. Replace the most recently used. Very easy. 1 is there 1 present? Okay, not present. Page fault. 1. 2, 3 present, not present. Page fault. Bring it from logical address space to physical address space. 2 not present. Bring it. Fault. 4 not present. Bring it from logical address space to physical address space. 5 not present. Okay, which one will you replace? The one which is recently used. 4. Most recently used. 4. 4 with 5. Done. This is the easiest. Most recently used is the easiest, isn't it? 3. Is there 3? 3 is there. Page hit. 1 is there. Hit. Isn't it? 2 is there. Hit. 1 again hit. 4 is there. No, 4 is not there. 1 most recently used is 1, isn't it? 1 with 4. Replace 1 with 4. Done. This was fault. 3 it is there. Hit. 5 it is there. Hit. Very easy. Very easy. This was the easiest one, isn't it? See, 1, 2, 3, 4, 5, 6. 6 page faults are there. How many page hits are there? 1, 2, 3, 4, 5, 6. 6 page hits are there. Okay. I hope FIFO, optimal replacement algorithm, least recently used and most recently used. These 4 algorithms are clear to all of you. Okay. Now let's see this one. Last 2 points. These are just theoretical points. I'll just tell you orally. See, we are done with all these things. Done with all these things. So I'll just tick mark it. Done with FIFO, first in, first out, page replacement algorithm, optimal page replacement algorithm, least recently used page replacement algorithm, and most recently used page replacement algorithm. In case of FIFO, there's something called as, okay, you can observe this phenomenon called as Bellardi's anomaly. Okay, see, I'll talk about Bellardi's anomaly. Beladi's anomaly. See, Beladi's anomaly indicates what? If there are, let's say, by increasing frames, number of frames, if page faults increase, then that particular condition is called as Beladi's anomaly. See, when we increase number of frames, obviously, you might think that page faults will decrease because you have increased number of frames, isn't it? Now, page replacement will be less. Now, instead of it, if reverse happens, by increasing number of frames, earlier, these examples which you did, they were with what? 4 frames, isn't it? This example 4 frames. This example is also 4 frames. For same reference string, by increasing number of frames, if page faults, instead of decreasing, if it increase, that phenomenon is called as what? Beladi's anomaly. It might happen, isn't it? I don't say that it will always happen. It might happen, isn't it? If it happens, that phenomenon is called as what? Beladi's anomaly. That thing, okay? It is called as Beladi's anomaly. You can observe it in FIFO, okay? Done with Beladi's anomaly as well. Now last concept, thrashing. Let's see thrashing. Last concept of this session, I think last slide also, okay. See this thrashing concept, very easy. Last point. Throughput of the system, degree of multiprogramming. Programming. Okay. This is x-axis, this is y-axis. Okay. Now, if you observe this one, as the degree of multiprogramming increases, throughput also increases. But after some threshold, let's say lambda, okay, the throughput keeps on decreasing when we increase degree of multiprogramming further. This particular stage, when we increase degree of multiprogramming, but throughput is, instead of increasing, it starts to decrease. This particular stage, okay, this is called as thrashing. Why this happens? Okay, when we increase degree of multiprogramming indicates what? Lots of processes come into main memory. Okay? Long-term scheduler will bring process to main memory, isn't it? Ready state. Long-term scheduler will bring it from new to ready state. If long-term scheduler brings lot of process in ready state, what will happen? Process will spend after this certain threshold. Instead of increasing throughput, it will start decreasing. Why? Because pages will spend more time in page replacement. That is why the throughput will decrease. Thrashing phenomenon occurs when you increase degree of multiprogramming, but throughput starts to decrease after a certain threshold. Then that particular condition is called as thrashing, in which processes will, it will spend time in page replacement, isn't it? This process will spend time, the page replacement will work continuously. That will happen. So that's about thrashing, isn't it? After some threshold. After some threshold, instead of increasing throughput starts to decrease. This condition is called as thrashing. How can you just avoid this phenomenon of thrashing? If you observe carefully, why is thrashing happening? When we increase number of processes present in main memory. Okay, who controls this one? Long-term scheduler will bring from new to ready state, bring into main memory. Long-term scheduler can control it, isn't it? Or you can also tell mid-term scheduler to suspend some of the process. Ready state to suspend ready state, isn't it? Are you getting it? Mid-term scheduler can suspend some of the process and control thrashing. Or long-term scheduler will just bring limited number of process till this threshold point, not bring more than that. That way you can avoid thrashing. I hope you got it, how to avoid thrashing. That's it for this video. If you observe this one, we have covered this topic of thrashing as well. Done with this one. Let me just show you first two pages. See, we saw all this memory management technique, contiguous memory management techniques, non-contiguous memory management technique today in this entire video. This video is super useful. Okay, just view this video one more time. If you did not get any point, just view it once again. Very easy. We saw fixed partition scheme, variable partition scheme. Then we saw non-contiguous memory management techniques like paging, multi-level paging, segmentation, segmented paging, inverted paging, demand paging. Okay. Then we saw this as well. We saw FIFO, page replacement algorithms like FIFO, optimal page replacement, least recently used, most recently used. We saw phenomena such as Bell-Ladies anomaly and thrashing. These two phenomena also we saw, isn't it? So I think we are pretty much done with everything. What was today's agenda? I have completed that today's agenda completely. Fine. So that's it for this video. I hope you like this particular video. Thank you so much. Bye.